Okay, we today are going to get into V substitution. It's different from U sub, which is it's a different style of solving first order differential equations. Normally, I would spend like a handful of days on this, and we would make them like actually pretty complicated, like kind of like an algebraic nightmare. Instead, we're gonna just look at the topic quickly and see how it works and do some more simple ones. Um, so this is the first one we're going to solve. My plan is to go through this one, like just kind of showing you how to do it, and then to do two more that are like more board work style, like you've done a bunch with me. But before I actually begin to solve this, I want to talk about two things that it is not. One, oops, it is not linear, which means that mu won't work. Mu is not going to work. What do I mean by it's not linear? Well, look, I got a y and a y prime. This y prime right here is with respect to x. I could write dy dx there instead. X is my independent variable. And look at this y here, right? That y is inside of a square. Remember, in order to use mu, I need to have a linear first order equation, right? This is first order, but it's not linear because that y is inside of a squared function. So that means I can't use mu. So what about, can I use separation of variables? Well, this is not it's not separable. You could try all you want. The fundamental problem here with it not being separable is that there's a plus sign right here holding these two together, and then there's a multiplication here holding these guys together. You could like factor stuff out, but then you would always you could just go in circles trying to separate y's on one side, then x's on the other. For example, I could take this y squared and then move it over here, right? But then if I were to factor a 2x out, then I would have a over 2x in this y squared, right? Or you could like, all right, let's divide by 2x, move it over there. And then look, that y squared is going to be trapped, right? So we could go through all those details, but I think you should see that I can't separate variables in this thing. So that means that I need a different method from the two that we've talked about so far in this unit. So I am gonna take a couple steps and then you'll see what this substitution is. So the first thing that I'm gonna do is sort of get y prime all by itself. It's kind of like normalizing in the other unit that we did, or in the other section that we did. So I'm gonna divide by 2xy, divide by 2xy, divide by 2xy. From here, what I want you to see is we get a y prime by itself on the left side, and then, all right, what cancels here? This cancels with one of those. The 2's cancel here. And then this y cancels with one of those. So what I'm left with is x over 2y plus 2, oops, the 2's gone, y over x. So what do you see? I see a y over x and an x over y. Now, your book actually gets into a lot of different ways that I can do a substitution, but the ones that we're going to focus on is where I introduce a variable v. So I'm going to say let v equal, and in this case, I'm going to let it be y over x. That's the only sub that you're going to do. There are some other, you can do like x plus y, you can do like trig functions if you want, but for this, we're just going to focus on the y over x. That's what I normally do in this class. So from here, I'm going to multiply by x. I think you'll see y. So this gives me v times x equals y. And then the next step, I'm going to derive with respect to x. Why am I doing that? Well, look, you should see that this guy, if I let v equal y over x, is going to turn into a v, right? But look, I've got a y prime here, right? Basically, when I sub all this stuff in, I don't want to have any y's left in my equation, but I want it to be equivalent, right? So you'll see how that happens because I'm going to take the derivative here. Notice I've got multiplication right there, so I got to use product rule. Well, I'm going to derive with respect to x, so that means dv over dx, that's the derivative of the first, times the second is x, plus v times, this would be the first times the derivative of the second. Well, what's the derivative of x with respect to x? Is just 1. So I just actually got a v there. And then equals, what's the derivative of y with respect to x? Well, it's dy dx. So this step, I'm going to put a little box around it. Whenever you do a substitution, you need to say what you're substituting. You need to show the work for finding derivatives, and then you need to and then have these three equations: this, and this. Since all the ones that I'm going to give you will be subs with y over x, this orange box should be in all of your problems. So now let's do some color coding. This is this guy, so that's going to be a v. This here, whoops, this guy is y prime, so that's dy dx right here. So that's actually going to get replaced with all this. And now, I guess, maybe I'll write over here, because the question is, what happens with this guy? Well, I got x over y. Well, that is equal to y over x if I write to the negative 1 power. So this right here is going to be v to the negative 1. So let me do that sub in. I get yellow is this. So I get dv dx equals, times x plus v equals I'll write it as 1/2 v to the negative 1. I could write 1 over v as well, plus v. That's the green piece right there. So when I do all this sub, it actually simplifies this equation significantly. It looked like this. It was kind of messy. And now look, all the squareds are gone, right? This guy right here actually cancels with that guy right there. And then I've just got this dv dx times x equals 1 over 2v. Notice this is now a separable differential equation, right? I got derivative v with respect to x, v, I can multiply, divide, stuff like that. So what that gives me is 2v dv equals dx over x. Now I can integrate both sides. On the left side, I'm integrating with respect to v. On the right side, I'm integrating with respect to x. So power rule on this side, v squared equals ln absolute value x plus a constant. Now I'm going to square root both sides. So that gives me v equals plus or minus, don't forget your plus or minus, square root of ln x plus c. Then I can go ahead and re-sub in. So here's the deal. My original problem was with x's and y's. I introduced this v, I brought it out of nowhere. I need to give my answer in the form of the original variables, right? Not in terms of this v. So I'm going to use this definition of v right here, v equals y over x, to replace this guy right here. So that gives me y over x equals, right side doesn't change, and then I can multiply by x to get y equals x, well, I should put my plus or minus out front, plus or minus x times the root of ln x plus c. You also could have from this line, actually here, I'll just pause. Totally legitimate to do this step, sub in the v to get rid of the v to turn it into y's and x's in here. So I could have done that and then multiply by x squared and then square rooted. And you can see that you should see that this line and that line are equivalent because I could pull this x squared out and put it here. would square root it and give me this x like that. So this is correct. This is correct. There's other forms that are correct. And I would take all of them, but I have a couple conditions. One, if you can solve for y, I'd like you to. Sometimes you can't. In this case, we can. And then it's nice to have it in the most simple form. If you can't solve for y, if it's impossible, then you can give it to me in a good simplified form. But actually, I don't think we're going to run into that too much. So, ba-boom, ba-boom. Now, I am going to... Okay, so just for the sake of convincing you that this is true, that this thing is actually the solution to this thing, that this right here is the solution to this, I sort of painfully went through this process of like trying to show that it worked. I took this and I took its derivative. I used product rule and got this giant mess in green. And then I started plugging it into this thing here. And I was like, oh my God, this is terrible. And then I said to myself, well, why don't I try using implicit differentiation? So I basically took this line right here and took its derivative. So you can see that line's there. And it actually worked out really well. So here, let me just bring this down to here. We'll move over a little bit. So I got this guy. That was a copy of this line here. I used implicit differentiation. You can double check this. 2y prime equals, and then there's some product rule here. That gave me 2y prime equals this, right? And then I said to myself, I recognize 2y prime. And I said, oh, that's like almost what they had on the left side here. So I multiplied that by x, right, to get this left-hand side. That gave me 2x squared ln of x plus 2cx squared plus x squared. It looks terrible, but if I go a little bit further, I say, oh, there's a 2 here, because I'm trying to build this over here. So 2 here, there's an x squared. I can factor it out of each of these terms, and I get x squared times ln of x plus c, like that. And then I said, oh, snap. X squared ln of x plus c, that's y squared. So I can actually just replace that with a y squared, and boom, this line and that line, they're the same thing. So you should see that this, whatever it means, it doesn't really mean anything, but this here is the solution to that differential equation right there. So hopefully that makes sense, and I'm going to give you a couple more to do in 2 or 1 more videos.